Today we are going to discuss about the high resolution electron microscopy or HRTM in details. In the last lecture, I have shown you the microscope with different parts of the microscope as well as different operations of the normal electron microscope. And in this class, we are going to discuss first what is the basic meaning of high resolution microscope and how such a microscopic characterization technique can be used for different purposes. So, first we will show you some of these examples which I have even shown you in the class 1 before the last one. This one is basically an image taken on cobalt and gallium doped zinc oxide. Left hand side of the image shows the normal bright field image of zinc oxide doped with cobalt and gallium with a electron diffraction pattern taken along 0001 zone axis. The right hand side of the image is basically taken from one such crystal showing the lattice fringes, that is the columns of the atoms are clearly shown. In fact, if we measure the distance between the two atomic layers, it should come as the d spacing of 0001 plane of zinc gallium cobalt doped zinc oxide. The next one is the little picture of same crystal shown as bright dots. In the last picture you have seen the lattice fringe, that is the different lines showing the columns of atoms. Here you can see white and the black dots as the signature of columns of atoms. So, but we do not know which atoms stands for what particular element, but we can clearly see the atoms very nicely. These images are taken in normal conventional high resolution electron microscopes with the fake or field emission gun control machines. The next image is again taken from CDS crystal, the cadmium sulfide, where you can see a very small crystallites about approximately 4 to 5 nanometer diameter, where each white dots signifies a column of atom. Similarly, black dots which are not observed clearly also signifies a particular column of atoms. The high resolution microscopy has evolved quite a lot. As we stand today, we can actually have very high power aberration corrected high resolution microscope, in which we can even see different atomic arrangements which are not possible even few years back. The left picture shows the silicon crystals. You can even see clearly the silicon dumbbells. We know that silicon dumbbells forms inside the crystals. The silicon atomic dumbbells can be easily deciphered from this picture. Right hand side shows even the information limits or resolution level rather of 0.8 Armstrong, the distance between the centers of the two atoms in the dumbbell structure. The bottom picture shows the strontium titanate or SrTiO2, where this A shows the atomic positions along certain crystallographic directions, B shows conventional high resolution electron microscopic image, where you cannot even see different atomic species properly because of the resolution problems. On the other hand, the C shows the different atomic species. Even one can see strontium, which are the big atoms like this, the white color. The titanium, titanium is basically sitting like this, that one can even see the oxygen atoms there. Residual contrast coming from oxygen atom can be seen, because these are all aberration corrected microscopy in COS detector is used. We will all discuss this thing in detail in subsequent lecture. If one is very careful, even one can see the vacancy in the oxygen atom positions. So, therefore, this is the state of part today of high resolution microscopy. So, if you want to understand the high resolution microscopy in detail, we need to look at from a very simple picture of a imaging system. But I would like to tell you something more about high resolution microscopy, in the sense that among all the structural characterization techniques high resolution electron microscopy tells you the atomic structure along a particular incident electron beam directions to the atomic resolution level, which is not possible in any of these characterization techniques. So, not only that, as we know that if we can take this atomic scale images along different electron beam incident directions, then we can build up a 3-dimensional structure, and that 3-dimensional structure is what is exactly we develop from the X-ray diffraction or neutron diffraction studies. So, in the viewpoint, we can say that it is possible to obtain the structural informations from different directions of the incident electron beam in electron microscope, as well as also it is possible to build up a 3-dimensional structure to the atomic resolution level. So, normally electron microscope or conventional electron microscopes which we use nowadays has a resolution level of 1.2 to 1.6 angstroms, but with the help of aberration corrected electron microscope we can reach a resolution limit of 0.6, even better than that, 0.6 angstrom or even better than that. So, therefore, it is possible to obtain the structural information to that level, to the resolution levels of less than 1 angstrom is what makes high resolution electron microscopy so powerful technique. Obviously, as I have shown you pictures where you can see even atoms, actually we do not see the atoms, we see the potential of an atom. When an electron interacts with the material and it forms a particular image, and we see basically potential of the atom in the imaging plane, we do not see the atoms. But many people write in the textbook and even in the lectures that with quote and unquote we see atoms. Well, fine. So, these are all very good features of high resolution microscopy, that we can see atoms virtually, we can build up 3-dimensional structure, we can get even composition information at the atomic energy level, and we can do many other things, but it has its own problems like any other techniques. The potential of this technique is severely affected by the fact that we need to interpret the images. So, quantitative interpretation of the images makes this technique rather difficult one for many users, and it has been found that to quantitatively interpret an image we need to have a priori idea about the structure of the material, and therefore, high resolution electron microscopy is to some extent dependent on the many other techniques from where we can get a priori structure of the material, which is very valid in case of complex structure like quasicrystals or incommensurate material structures where we do not have any idea where the exactly atoms sit. So, therefore, describing the high resolution electron microscopic images quantitatively from those kind of crystals or those kinds of materials is a big challenge for us. Although advent of computers have made our life easy, but it is not very simple still so far. To run the simulations in a computer, one needs to have lot of a priori knowledge about the structure of the material, composition of the material, many other things which needs to be obtained from different other characterization techniques. So, by knowing all these aspects, let us now look at what is actually high resolution electron microscopy from the very basic point of view, and how we can understand it from the imaging tool of an electron microscopes. Let us start with a very simple thing, that is the camera or the camera obscura. In camera we know it is basically a black box, and in which we have a pinhole, and the light passes through this pinhole and from the image. So, therefore, if we have an image in the image plane like this, and we have a window or a small hole or called pinhole through which the light passes through, and we form an image there. This is what is basically a camera looks like. The obscure camera means the old camera. Modern day camera has many other lenses. So, therefore, if I have to describe this camera image formation in terms of mathematical aspects, so we can always assume that this image to be one dimensional, and the functions are very simple. So, let us do that. If we assume that image has object can be given by a function like f x, object is given by a function like f x, and this object is basically getting focused on the image plane while these rays are passing through the pinhole. So, therefore, the rays are passing through a small aperture, and if we assume this aperture to be the window through which the light is passing through, then we can interpret the image, basically the contribution of the point x in the image plane by this function called f image x, which is nothing but the a x minus x prime into f x prime dx integral. Okay, so, where a x minus x prime is nothing but the aperture function. So, that means if I want to get the image information or the informations in the image plane, we need to use the aperture function. Aperture actually modifies the image during formation. Now, this is very simple equation or very simple equation which is used in the imaging technique, which can be available in any books. You can actually take convolution of these two a x, and this equation can be written like this: a x convolution of a x and f x giving rise to the image function. So, this function integration of the aperture function and this object can be simplified like this, the convolution product of a x and f x. And obviously, any image whenever we form, we need to get the diffraction information, one needs to do the Fourier transformation. So, in the Fourier space, this expression can be written like this: f I m into g, where g is the spectral frequency. So, a g is convolution of a g and x g. So, we know that convolution of any function once we transfer into Fourier space remains the convolution of the Fourier components, where g is basically now the spatial frequency. So, g is nothing but a spatial frequency, because in the Fourier space everything is described in terms of frequency or inverse of lambda. And a g, or rather let us write like this to depict it, the Fourier space, a g is given known as Fourier transform of a x can be given as known as modulation transfer function, or known as also the modulation transfer function of the imaging device. So, this is a very important aspect of any imaging device, because the whatever is getting image from the object plane to the image plane is getting modified by this aperture function. So, any simple camera, if we see the image, even though we are assuming that the whatever is there in the object is getting directly projected into the image plane, is not true. So, this is what actually dictates many things, like resolution of the imaging instruments and the information level of the imaging instruments and many other aspects. So, every imaging device is, that is why I said, is characterized by this function called modulation transfer function, or simply called transfer function in the books. It describes basically magnitudes of the spectral frequency, or g, which is getting transferred to this device from the image object planes to the image plane. So, how much of this magnitudes or the values of this spectral frequency which are present in the object is getting transferred to the image plane via this device is what tells you the transfer function. So, we will discuss more about the transfer function in the subsequent slides. So, let me just tell you something about also resolution, which can be easily derived from this picture. But once we go to the next slide, it will be clear. So, let us suppose that mathematically this is the image, the object function f x as a function of x in one dimensional. So, you can see lot of spikes and lot of basically other things, and if we just take this Fourier transformation of this f g, it becomes a very discrete peaks in this Fourier space, because this has transferred from the image space to the Fourier space. So, therefore, everything is a function of frequency, and we can always say the aperture function is like this as shown in this picture. So, aperture function is 1 in the aperture and 0 everywhere else, because this is a small hole through which the light is passing through. So, therefore, any places outside the small hole, light is unable to pass through, therefore, we can assume this to be 1 in the aperture, 0 in other places. And if I just Fourier transform this again gives me a lot of peaks. Okay. Now, if I take the convolution of f x and a x, it becomes a function like this with a frequency with a Pascal distribution. So, which is summation nothing but is in this and this, and most importantly, if I take convolution of f g and a g, it gives me 1, 2, 3 peaks here, which are basically can be called as the signal in a basically any imaging device. So, therefore, whatever there in the object space is can only be converted into the image space once you have very nice signal coming out of there. This is what actually seen or observed mathematically when we transfer any points in the object planes to the image plane through the aperture function or through any imaging device other way. And TM or HRTM is consisting of many imaging plates or imaging imaging lenses. So, therefore, for each of the lens there is an imaging function or transfer function. So, and they are all cumulatively added. So, therefore, the total image quality of image which you obtain after the object passes, the light passes through or the electron beam passes through all these lenses is basically can be obtained if we have convolution of all these the aperture functions in this Fourier space. So, this allows us to basically define the resolution. So, resolution is basically of an imaging instrument is defined as a cutoff or 1 by cutoff means 1 by rho cutoff in the that means this is the 1 by rho cutoff which tells you the distance difference between the signal and the noise. So, if I take the ratio of signal and noise, there is a cutoff below which nothing can be transferred by the imaging device. So, any other frequencies spatial frequencies here above this 1 by rho values which are marked here can no longer be transferred by the imaging device. So, this sets us the resolution. This resolution actually is basically can be easily compared with the Rayleigh's definition of resolution which I have discussed in the class 2-3 class before. So, this is basically in a physical sense definition of resolution of any machine. Now, Fourier transformation of this transfer function basically or this AG or rather whatever we have said is basically known as the Laplace transfer function, which we will discuss later. This is nothing but generalization of the aperture function of the camera. It is basically you have seen here you can see this there here also you can see that this is basically sharply peaked plot of the as a function of FG convoluted AG as a function of the 1 by wavelength or the reciprocal space. So, therefore, the width of this function basically can be related to the Rayleigh's resolution criteria. Now, this is very simple and as I said the resolution can be easily plotted like this. So, therefore, if I plot this is as a resolution in the x axis or the signal actually not x axis. So, if you clearly see that this is the noise level. So, therefore, any frequency or any spatial frequency beyond 1 by rho can no longer be transferred by this imaging device into the image plane. So, therefore, we tell this is the resolution of the imaging device. So, all the other frequencies, all the other values of G spatial frequencies can be easily transferred by the machine or by the imaging device, whether it is a camera or electron microscope. It can be transferred into the image plane, and that is why this can be defined as the resolution of the machine. So, now theoretically these are all possible. Practically no microscope is a perfect one, or no camera is also a perfect one. There are a lot of defects inside it, and these defects do play a serious role in basically reducing the resolution level from these to even low, much higher. So, let us now discuss, by knowing this so these aspects very well, let us now discuss about the electron microscopes. This is basically very simple thought I just gave you at the beginning of this lecture. Let us now talk about the image formation in an electron microscope. We know the image formation in electron microscope is a coherent process. What does it mean? Object as well as the transfer functions in the electron microscopes are very complex functions, and they are complex functions of both the complex function with an amplitude and also a phase component, because they are all waves. So, like any other waves, there will be amplitude component, there will be basically a phase component. So, as we know that wave function, so whenever if you think of an object in electron microscopes or sample electron microscopes, we know that electron beams falls on the sample and passes through the sample also, because it is a very thin one. So, if I think of that, this is a sample in the electron microscope, and electron beam falls like this and interacts, and then either get diffracted or not get diffracted through this exit plane. Okay. So, by knowing this is what happens in electron microscope. I discussed with you in the class before. By knowing this, now if we think that wave function or electron wave function basically is at the exit plane is given by this, we can always write this, where basically the r is the exit plane and psi is the function or electron wave functions. So, if I have this kind of consideration, we can always think this wave function is explained as a planar source of the spherical waves. Okay, these are the planar source of the spherical waves here at the exit plane. Huggian types, we can always do that, and obviously then in that case, if they are all planar source of the source of light or electron at the exit plane. So, we can think of that the sample is acting as a grating or diffracting grating, and then according to Fraunhofer's diffraction theory, Fraunhofer was one of the scientists who basically worked tremendously on the diffraction theory. According to his theory, the complex magnitude of the diffracted wave is in the direction of wherever the electron beam is going. This direction can be, the diffractive direction can be given by certain value of the reciprocal vector. So, therefore, we can always tell from the Fraunhofer diffraction theory that complex aperture diffracted wave in a direction given by the any reciprocal lattice vector can be written given by the Fourier transformation of the object function. So, if this is the object function, if I take a Fourier transformation of this object function, that is this is nothing but the diffracted beam or the what is called the diffracted beam intensity this. This is what is called the Fraunhofer diffraction theory tells us from the very basic knowledge. Now, in an electron microscopes, we know that objective lens. So, let me just go there. We know that objective lens actually placed behind the sample. That is what you see here. This is the objective lens here in the microscope, here also. So, sample is basically immersed in the objective lens, as I told you in the class and shown you in the while showing the microscopes. So, objective lens is basically behind the object. Therefore, it focuses all these waves into a plane called a black focal plane. Okay. And that is also shown here. This is the black focal plane you can see here. It basically all the whatever waves coming out of the exit planes, they are focused by the objective lens onto a black focal plane. and then actually these positions of this this focus beams gives you basically diffracted spots or diffraction beams rather. And when these diffraction beams has then focused on the or rather form the image on the imaging plane, we get a diffraction pattern. Therefore, back focal plane of the objective lens contains the Fourier transformations of the object basically, if you think of it that way. In the electron microscope, we can change actually, that is what we have shown you, we can change the settings of the electron microscope, rather we can change actually the focal length of these different lenses like intermediate or the first intermediate lens to either focus this back focal plane onto the image plane and see to obtain these to see these diffraction patterns. And obviously, the intensity of these diffraction beams will be intensities will be proportional to square of this Fourier transformation of this the exit wave in the Fourier plane. And in if the object is periodic, that is a crystal, then diffraction pattern will be periodic. The object is continuous, diffraction pattern will be continuous. These are all understandable. This is the basically classic sense of diffraction pattern formations in a classical TEM. So, that is normally routinely done in the microscopes. Whenever we insert a sample, first thing we enter crystals and then put the aperture in for the select aperture in and get the diffraction pattern. That any electron microscope users who are seriously doing the microscopy can immediately recognize this whenever whenever he or she goes to the microscopes. There is a second kind of stage of image formation. This is the first kind of image formations, and in fact actually one can use these diffraction patterns to do diffraction contrast imaging, which I will talk within moments time. So, in a second set of image formations, the back focal plane can basically can be thought of acting as a set of Huygens sources of the spherical waves. We can always think of they are acting actually as a set of Huygens sources or the sources of the electron beam as spherical waves, which can be then allowed to interfere. So, if these diffraction spots are allowed to interfere, and then it can form the interference patterns on the image plane. So, whenever that happens, we get something what is called lattice fringe images, which I shown you in the beginning of the lecture. So, this basically is called whatever by forming this by interfering this set of Huygens spherical waves and then forming a lattice fringe wave. Lattice fringe is nothing but inverse Fourier transformation, which basically reconstruct the object function psi r in the image plane. So, therefore, by just looking at the camera picture and comparing it with the electron microscope, one can simply understand how these basic things actually happens in electron microscope. Let me just show you how the electron diffraction pattern form. As I said, if I have a object here, the objective lens basically focuses all these the diffracted beams into the back focal plane, and that is what we get diffraction spots when we basically image this the diffraction spots or focus the diffraction spot basically on the image plane. So, this is simple like formation of nothing but Fourier transformation of the electron beams or the exit waves at the back or the exit surface of the crystal. So, now once we can use, as I said, we can use this diffraction pattern to image or get diffraction contrast, which is normally done in the electron microscope, standard electron microscopes. So, this is my diffraction pattern on the back focal plane, okay, as you can see, focused by the objective lens. This is the objective lens here, and this is the diffraction pattern on the back focal plane. So, if I take the bright spot or the undiffracted spot or the transmitted spot or the forward scatter spot, whatever way you can explain, then whatever we form is nothing but a bright field image, and the field is bright and the image looks black. On the other hand, if I take any of the diffracted beam here like this and use this to form the diffracted the image, then what you get is a dark field image. In the field of view is dark, image is basically bright, and this is what is shown here in this way. So, by using the aperture, objective aperture, we can either form the bright field image or you can form a dark field image, and this is routinely done in electron microscopes. anyone who is doing normal series microscopy are very well conversant with this. On the other hand, what I am saying is the second sort of imaging process, just a few minutes back I discussed, is nothing but if I use all these diffracted and the transmitted beams and allow them to interfere, and then I form what is known as a lattice fringe or lattice image. This is what is shown here. You could see that I have marked a larger area, or I put a bigger aperture in the diffraction pattern and selected at least 8 diffracted spot along with the transmitted spot, and we can form this kind of the phase contrast images. So, this is the second set of the imaging formation which is done routinely in electron microscopes nowadays, because of the advent of different high quality microscopes. This is now also can be done routinely. So, as you can see that in a real practice, by putting an aperture in the focal plane of the objective lens, it is possible to form either a phase contrast or interfere phase contrast image, which is basically nothing but the interference of these diffracted and transmitted electron beams from the back focal plane, or we can select one of these basically transmitted beam or the diffracted beam and then disallow this interference to happen and form the images. But as I told you, electron microscope, like any other objects in this world which man makes, is not a perfect device. So, therefore, anything, any wave which is passing through this objective lens, any electron wave, it undergoes a phase shift and also amplitude reduction, and amplitude reduction is nothing but a damping. Therefore, we need to consider the transfer functions of the objective lens to really describe actual image, and this is what we will do it. A transfer function in objective lens or objective electron microscope in objective lens can be written or can be given in a very simplified way. I will not discuss the detailed derivation of that, but transfer function can be written very easily. So, if I write transfer function in a electron objective lens like this, Tg is nothing but 2 Ag, G is the spatial frequency, and sin xi z. So, this is what is basically simplified transfer function in an electron microscope of the objective lens, where Ag is basically tells us the effect of or the aperture function, effect of beam selecting aperture, and psi z, which is very important parameter here, is basically phase shift. It tells us the phase shift, and Ag is the aperture function. So, this is a very important functions of the objective lens in electron microscope. This will tell us not only the resolution, but also the information limit which you can obtain in the high resolution electron microscope. That is what I am telling. So, wave function at the image plane obviously can be written like a very simplified wave function can be written like this. This is wave function in the image plane is if it is R, then can be written as inverse Fourier transformation. So, inverse Fourier transformation is like this, inverse transformation of the transfer function and the psi z, and intensity obviously will be proportional to square of the wave function, that we know. So, that is therefore, and this is very simplified theory. We assume in this theory that the crystal is very very thin. So, there is no interaction between these diffracted beams inside the crystals. Once they come out, then they interfere from the image. So, that is not all, this is what is called as a coherent approximation. So, if you assume the coherent approximation, then only this formula is correct, otherwise the formula gets complicated, and those complicated formula needs to be derived based on the concept of transmission cross coefficients. Okay, how this the beams are actually interacting, and because of that there is a cross coefficients. So, if you know the transmission cross coefficient, then we can actually see this function then will be much more complex, which I can actually give you. So, psi r can be written as integration of g plus g prime into multiplied by transfer function g plus g prime g into psi z g. That basically tells you the interaction between these two different spatial frequencies g and g prime. So, forget about it, we are not going to use this, we are going to use the coherent approximation, and for that the what is called wave function at the image plane can be calculated using inverse Fourier transformation of the transfer function and the psi z. Well, by knowing this, now actually one can seriously look at the exact nature of this phase shift or the psi z function, which we are going to do in the today's lecture very seriously. And that is basically the purpose, because this will tell us many important aspects of the image formation. So, as you see that psi z, as I said, this goes into the transfer function very importantly. This is the aperture function. So, aperture function can be derived as I showed you in any electron micro any device, but let us first look at what is the nature of this function. The studies indicate that psi z is basically depends on three factors, or it actually has a combined effect of Cs, the spherical aberration constant of the lens. As I said, any lens is not a perfect lens. So, like in a camera also, we know that lenses have spherical aberrations, mostly spherical aberrations. Chromatic aberration also comes into picture, because chromatic aberrations comes from the difference in the energy levels of the incident electron beam, but let us, for the sake of understanding or the simplicity, assume that spherical aberration is the most important defect, and then second factor is the delta f or the focus, and third factor is what is known as, or this is the delta f is the focus, which is basically the depth, the objective lens defocus, and third factor is obviously the wavelength. We will see that, and they are all Cs and wavelength are related, we will see also that. So, if we can consider, we can find out a point at the specimen. Okay, basically what does it mean? The effect of this on the psi z means that if I have a point in the image plane, that point will be focused as a disk because of the effect of spherical aberration and the focal length or the defocus of the objective. So, therefore, we can basically tell that you know the image whatever has been formed on the image plane as a disk can be given by this radius delta theta equal to Cs theta q plus delta f theta. This function tells us the disk which is formed. So, if you want disk to be small, then you want Cs and delta f to be optimized, and that is can be done by analyzing the whole problem mathematically, which we will do the next 10 minutes or so finally. So, we are discussing about this effect of the different parameters on psi z. So, let me just describe it in detail all that. As I said that psi z, this function which is going to the transfer function very as a factor, depends on three aspects: the Cs, the spherical aberration constant, defocus of the objective lens, and the astigmatism of the objective lens. So, astigmatism can be easily corrected, as you know, even in normal camera also astigmatism can be corrected, but these two parameters Cs and delta f, they need to be optimized to basically have the best value of transfer function, so that we can obtain very good resolution in the images. Now, we shall go through a very simple exercise to derive the value of this psi z. Let us do that. And as I said that the basically the exercise is nothing but the combining this effect of CS and the defocus of the orbital lengths. So, if I do that, we find that any object, any point in the object normally will be focused onto the image plane like a disk, because of this presence of the CS and the delta f. And so, therefore, we can write down the diameter of the disk as delta theta to be equal to CS theta q plus delta f into theta. And so, basically the rays which are passing to the objective lens, they at an angle theta are not focused to the same point, okay, because of the spherical aberrations and finite value of the delta f. That is why they are basically coming at that. But we know that not only one value of theta we need to consider, but we need to consider all the values of theta. Theta is nothing but the diffraction angle. So, therefore, we need to consider all the diffraction angles, and in that case we need to average out the value this value as a function of the diffraction angle, and which can be done by simply doing the integration of this equation from 0 to theta CS theta q plus delta f theta d theta. And as you can see, if we once integrate this equation, one can get this as a CS theta to the power 4 by 4 plus f delta f by 2 into theta square. This is what is the basically the disk, average disk diameter. If we integrate this, we can get. Now, we know that from Bragg's law, that we can very easily write from Bragg's law that 2d sin theta b equal to n lambda. So, therefore, we can write down for Tm, basically for normal microscope, we know theta is very small. If theta is very small, then we can write down 2 theta b sin theta equal to almost like theta equal to, we can write down very simply that lambda into z, where g is basically 1 by 2d. You can see that g is 1 by 2d, which is the reciprocal space. G is 1 by d actually, which is the reciprocal lattice vector. So, if this is the case, the 2 theta p is basically very specific value, because this is the diffraction scattering angle for the diffraction to happen. Now, we can insert this what's called value into this function, and then we can get the whole function like this, the psi z. Psi z is the phase that is equal to d 2 lambda by 2 pi by lambda into d g, and this is nothing but then 2 pi by lambda into CS theta to the power 4 theta to the power CS theta to the power 4 by 4 plus delta f theta square by 2, and this can be easily written in a mass simplified form like this. So, delta f into delta f by delta f into lambda square. No, we can convert this theta into lambda, as you can see from there. So, therefore, we can finally get this to be equal to twice pi by lambda into CS lambda 4 and G4 by 4 plus delta f into lambda g by 2 theta b, that is equal to lambda square g square by 2. So, that basically gives me the value of psi z, and therefore, that means psi basically this psi is basically a function of pi, or psi can be written as a pi delta f lambda pi delta L lambda into g square plus Cs half phi into Cs lambda to the power 3 and g to the power 4. So, what you can see is a very complex nature of this function psi, and if I take a sine of this, that becomes a very simple complex function, and it is very difficult to even calculate these functions normal simple mathematical way. We need to use certain tools to calculate that, but whatever you see that the psi depends on not only the delta f lambda and g, okay, depends on delta f lambda g, but also Cs very strongly. So, that is why one needs to optimize the delta f and the Cs in electron microscope very clearly. And in the next, and basically ideally the transfer function should be like this, from 0 to g1 it should have a specific value, and beyond that it will be all 0. This is the ideal transfer function in electron microscope, but this is never possible. So, if I plot this transfer function as a function of z here, generalized functions, okay, obviously it depends on the values of delta f, the lambda and Cs. If I consider Cs to be 1 millimeter and delta f to be minus 58 nanometers, and E0, that is the electron beam by the radiation, the voltage by which the electron beam is accelerated is to be 200 kilo electron volts, then this is the nature of Tg. So, you can see that it's not, doesn't look like the ideal nature, rather it's basically from 0 it goes down, the increases, there are a lot of crossovers, that makes the life very difficult. Now, let us look at the nature of this curve as different functions. So, the next one is basically as a function of Cs. So, if you can see, if we increase the Cs from 1 to 2 to 3, the function nature is totally changing. As you can see here, for the value of 1, which is very low for Cs, with a particular value of the accelerating voltage and the defocus, we can see that there are different crossover. Crossover here is basically crossover there is coming at different values of g. Even one can even see that crossover is basically changing, basically coming at a lower value of g as you increase the value of Cs. Now, if we keep the Cs to be 1 millimeter, because that is what the best possible we have seen, and then vary the focus, vary the defocus from 30 to 50 to 70 minus a nanometer, and one can see that how these things are changing. In fact, one can see as you go from minus 30 to minus 50, basically this width is changing, the G1 is also changing, the crossover point at which this transfer function is 0 is also changing. But once we go to very high defocus values, we can see there are two spikes coming into picture, one at G1, other at G2, and both of them are basically not meeting the line at 0. So, that makes the life very complicated. Therefore, what could have seen that these two parameters, the Cs and the delta f, has a strong role in basically in determining the transfer functions. And in electron microscope, Cs is obviously given by the orbital length configuration. Cs can never be changed. So, given a microscope, what we can change is the objective focal length or the delta f value, the defocus. So, in the next lecture, we are going to see the effect of defocus and how we can use this to obtain various informations in the high-resolution micrographs.